Hi friends, welcome to a new session on control engineering for undergraduates of 7th semester mechanical engineering. In module number 3, we have already studied about the steady state analysis. Now we are going to know about the transient response. Under transient response, we are going to know more about the specifications of transient response and the numericals based on transient response when they are subjected to unit step input, which is a standard type of step input. The general operation representation for this type of systems. Let's recall what is time response. As defined earlier, time response is the response of a control system and it is a function of time. We have already discussed in a time response systems we are being classified with the output, and those two classifications are the first one, the transient phase, and the second one is the steady state phase, or we call it as a transient response or a steady state response. Let's see the response for a given type of a system. It may be a second order system. Here we are having a curve of response. So this is the response axis and that is output axis, and this one is a time. So here the output is going to be changing with respect to time. So here there is output changes with respect to time. So here we can see a sinusoidal type of a wave generated. This type of a response where we see this part until where the change in output is happening, that particular part or that until that phase we call it as a transient phase. And if the output almost gets settled, or it is output is almost going to be remaining constant, or in other words if I tell the output is not going to change with respect to time, or there is a very little deviation in output with respect to time, and that particular time period or phase is called as a steady state. So regarding this we had already known about this one, but here we are going to talk more about the transient phase, where we are going to have the change in output with respect to time, and during this phase itself only what we are going to do, we are going to find the various specifications of the time response. Here we are going to talk more about time response specification. So specification for control system design often involves certain requirements which are associated with time, and time response of a closed system needs to be understood. The time response requirements are the behavior of the controlled variable or by the control error on a well-defined test signals. Hence, here in the time response specification we are going to talk about the specification of a second order system. The time response of a second order system for an underdamped case is shown in the figure below. Here we can see the figure of a underdamped second order system step response. Okay, here we are having two axes. One is related to the output, that is CT, and here one more the x-axis, which is a function of time. So the very important thing here to note is, here we are giving the test signal is a step input or a unit step input for the given system, and here we are going to understand the behavior of the output from the system. So in this one, for a unit step input, the need of an ideal output is like this. It should rise here and it should be settling, and need here is to be straight with respect to time. But here we can see the behavior of the response is going to be in a curve. So it is rising and it is going to overshoot the output. That is, here the input was step input, it's going to overshoot. This overshooting is happening because of the inertia of the input signal, and then it is going to settle down or damp down, and it is going to come back to its original position after a certain duration of time. So this is how we are going to see the settling of the signal happening towards the end, that is after a certain duration of time, and it is coming very near to the steady state band. So this is the steady state band or error band where it is going to settle down. So here we can see all the time domain specification represented in the figure, like the TD, TR, TP and TS, where TD stands for delay time, TR the rise time, TP the peak time, and TS the settling time or setting time. And here we are having the MP, the maximum peak output. So all the domain specification are represented in this figure. The response of the up to the settling time is known as the transient response, and response after the settling time is known as the steady state response. Means from here 0 till TS, this period is called as a transient response period, and after TS, this period is called as a steady state response period. Now let's understand or come across with the terminologies or the specifications of a time response one by one. Here, first one, we need to understand the delay time. The delay time is the time required for the response to reach half of its final value from 0 instant. It is denoted by TD between 0 and 1, and TD is given as 1 plus 0.7 zeta divided by omega n. So if you observe the figure here, so this is the 50% of the output. So this is, if 1 is the output here, the 50% of the output, the first time when it reaches to the 50% of output, the total time taken, this one we call it as a delay time or a TD. So it is measured in terms of seconds. So here it is given TD is equal to 1 plus 0.7 zeta divided by omega n. Next, rise time. It is the time required for the response to rise from 0% to 100% of its final value. This is applicable for under-damped system. For a over-damped system, the consideration of duration is from 10% to 90% of its final value. The rise time is denoted by a letter TR, and it is given by the expression TR is equal to pi minus tan inverse of root of 1 minus zeta square by zeta whole divided by omega d. So here omega d is the damped natural frequency. Okay, here zeta is the damping ratio. So here if I happen to see the diagram, the rise time will be till here, the first from 0 to 100% of its input, that is 100% here means 1, that is the output we are going. First time when we reach the output, that is that period of time, we call it as a rise time. Next, the peak time. It is the time required for the response to reach the first maximum or a peak value of the response, and it is measured by the TP, and it is given by TP is equal to pi divided by omega d. Here if you happen to see the diagram, so TP is this period, the first maximum peak output whatever you are going to get from the input. So this period we call it as a TP period. Next, maximum overshoot, that is at a TP period. It is defined as the difference between peak value of the response and the steady state value. It is usually expressed in a percentage of steady state value. If the time for peak is TP, then percentage peak overshoot is given by percentage m suffix p equal to exponential or e to the power minus pi zeta by root of 1 minus zeta square into 100. Here we are multiplying it by 100 because the peak overshoot is measured in terms of percentage. At TP, whatever height we are going to get from the steady state value, that is here. So from this particular part, to here, whatever height you are going to get, the difference what we get, this one we call it as the maximum peak output or peak overshoot. Next is the settling time. It is denoted by letter TS. Here the settling time is the time required for the response to reach and remain within a specified tolerance limit. Usually the tolerance limit set or accepted by the designers is plus or minus 2% of the output band. So here around the steady state value, plus or minus 2% is going to be treated as our settling time period when it is going to have this band. So for 5% error, TS is equal to 3 divided by zeta into omega n, and for a 2% error, TS is equal to 4 divided by zeta into omega n. This one we have already known when it is going to be substituted for different value of t in a steady state error. There we have understood about this one. Okay, so here I would like to tell you where we are going to have this one. Here when we are having the band, this is the band plus or minus usually 2% of the steady state. So this one, from this one 2% of steady state. Here we can see it is, here band is 5%, hence the value is going to fluctuate from minus 0.95 to 1.05. When this is going to start and it is going to remain this period, that period of time we call it as the band period, and where it started, that period is going to be called as a steady state period, and until that period we call it as a transient response. So to recap, delay time TD is equal to 1 plus 0.7 zeta divided by omega n. Rise time TR is equal to pi minus tan inverse of bracket root of 1 minus zeta square by zeta whole divided by omega d, where zeta is the damping ratio, pi is in terms of radians. Here then peak time Tp is equal to pi divided by omega d. Maximum overshoot MP, that is measured in percentage, hence MP is equal to exponential or e to the power minus pi zeta by root of 1 minus zeta square into 1 into 100. So this is exponential power. Students may make it wrong here, exponential power. So it is minus pi zeta by root of 1 minus zeta square into 100. Remember to multiply it by 100 to get it in terms of percentage. Next we are having the settling time. For 5% errors, TS is 3 divided by zeta into omega n, and for 2% error, TS is equal to 4 divided by zeta into omega n. Using these expressions, we are able to solve some numericals. Let's solve a simple numerical. Example: a unit feedback system is characterized by an open loop transfer function where the forward block g of s is given as k divided by s plus 10. Determine the gain k so that system will have a damping ratio of 0.5, that is zeta. For this value of k, determine the peak overshoot and time at peak overshoot. Both you have to determine. Here for a unit step input, so it is stated that it is going to have a unit step input for a given open loop transfer function. Let's begin. We are having the transfer function, that is C of s by R of s. So we are writing it as g of s divided by 1 plus g of s into h of s. Here g of s is k divided by s plus 10, so it is written here. Okay, 1 plus, it is 1 plus g of s into h of s. H of s here it is feedback, unit feedback system, so it is having a unit feedback system, hence h of s is equal to 1, so this one will be 1. After simplification we get k divided by s square plus 10s plus k. Now we are going to compare the above system with the standard form of second order transfer function. We have already known about what is a second order type of a transfer function when we are dealing with steady state error. So we know that second order transfer function is given as C of s by R of s is equal to omega n square by s square plus 2 omega n zeta into s plus omega n square. So comparing equation 1, this is equation 1, with the standard form of a second order transfer function, that is equation 2, we are knowing that here 10 is equivalent to 2 omega n zeta, and here omega n square equal to k. So whenever you are comparing, you have to compare the denominator part, keep it in mind. So comparing, we get omega n square equal to k, so this is omega n square equal to k, therefore omega n equal to root of k. Similarly 2 omega n zeta 2 omega n zeta or 2 zeta omega n, that is equal to 10. Hence 2 zeta omega n equal to 10. Therefore zeta is equal to 10 divided by 2 omega n. Omega n just now we have got, we can use that one. And moreover, the damping ratio, here we are having the damping ratio of value equal to 0.5 is given. This is the value of zeta, this is value of zeta, that is equal to 0.5. Hence given 0.5 equal to 10 divided by 2 times of root k. Therefore we get root k equal to 10. Squaring on both sides, we get k equal to 100. This is our gain value, k 100, the gain value. Now from this k equal to 100, if it is, then omega n equal to root of k will be equal to 10. Therefore omega n equal to 10 radians per second. So this is what we are going to get here. Now we need to find first the peak overshoot and time at peak overshoot. Hence first we know from the time response specification, peak overshoot MP is given by percentage MP is equal to e to the power minus pi zeta divided by root of 1 minus zeta square into 100. Substituting the value of zeta equal to 0.5 here, and here zeta equal to 0.5 square, what we get? We get a value after multiplication with 100, that is equal to 16.3%. So this is peak overshoot value. Now we need to find out at what time we are going to get this peak overshoot, that is the peak time, and it is given by Tp. We know Tp is equal to pi divided by omega d. So Tp is equal to pi value, that is 3.14. Omega d is equal to omega n into root of 1 minus zeta square. So we know omega n from the previous part, that is 10 radians per second. Substituting here, we get 10 root of 1 minus zeta square. Zeta value is 0.5. Here the peak time Tp is equal to 0.36 seconds. So at 0.36 seconds we are going to get a peak overshoot of 16.3% for the given problem. Let's solve another problem. Here in this example 2, the problem statement is as follows. A unit feedback system is characterized by an open loop transfer function. Here g of s, that is forward block, g of s equal to 10 divided by s square plus 5s plus 6. Determine the following quantities of it when it is subjected to unit step input. First, find the undamped natural frequency, means we need to find omega d. Second, damping ratio, that is zeta. Then third, peak overshoot, that is percentage of peak overshoot, that is NP. Then peak time, means time at a peak overshoot, that is TP. And a setting time or settling time, it is TS. This has to be found out. Let's do it. Here we are having the block representation for this one. We can do this one. The forward block here is 10 s square plus 5s plus 6. It is a unit feedback system, so hence it is 1. So it is having a closed loop system, so it is going to be having a minus. Hence what we get, C of s by r of s is equal to 10 divided by s square plus 5s plus 6 whole divided by 1 plus 10 divided by s square plus 5s plus 6. When we simplify, we get here 10 divided by s square plus 5s plus 16. So this is the value what we are going to get. Next, we need to compare the above system with the standard form of a second order transfer function, that is C of s by r of s equal to omega n square by s square plus 2 omega n zeta s plus omega n square. So when we compare here, we can see omega n square is equal to 16 and 2 omega n zeta is equal to 5. So on comparison, we get omega n square is equal to 16, therefore omega n is equal to 4 radians per second. Similarly, 2 zeta omega n equal to 5, hence zeta is equal to 5 divided by 2 omega n. Omega n, just now we got it, natural frequency, that is 4 radians per second. Substituting 5 divided by 2 into 4, the value will be zeta, that is a damping ratio, equal to 0.625. Using these two values, that is omega 1 and zeta, we are able to find the undamped natural frequency, which is omega d. Undamped natural frequency omega d is given as omega n into root of 1 minus zeta square. Omega n value is 4, root of 1 minus zeta square, just now got 0.625 square. So hence after simplification, we get a value of omega d, that is undamped natural frequency, equal to 3.12 radians per second. Next, we need to find the damping ratio, which we have already done. We can do it once again, that is damping ratio equal to 0.625. Next, we need to find out the peak overshoot. Peak overshoot, we know that it is given as percentage MP equal to e to the power minus pi zeta by root of 1 minus zeta square into 100 whole multiplied by 100. This has to be kept in mind, whole multiplied by 100. E to the power we have to do, then get the value, multiply. That is being shown here. So here we are having pi minus pi into 0.625 by root of 1 minus 0.625 square into 100. So the percentage what we have got here is 8.08 percentage. Next, we need to find out the peak time. Peak time at peak overshoot is given, Tp is equal to pi divided by omega d. Therefore Tp is equal to 3.14 divided by, we have omega d here, from here we are going to take omega d, that is 3.12 radians per second. So hence the value is very near to 1. Tp is equal to 1 second. Next, they are told about setting time or settling time. If they have not mentioned about what percentage error, so we can assume for a 5% of error. Assuming for a 5% of error, we have Ts is equal to 3 divided by zeta into omega n. Hence Ts is equal to 3 divided by zeta 0.625 into omega n 4. The settling time or setting time is for this type of system is 1.2 seconds. If we want to find it, or if suppose they tell it for 2 seconds, 2% error, Ts is equal to 4 divided by zeta into omega n. Hence Ts is equal to 4 by 0.625 into 4. We get for a 2% error, the settling time or setting time equal to 1.6 seconds. So these are the two different types of problems or related to the specifications of a transient response. For any details or for any queries, please do contact me at naveen.kalal@canaraengineering.in. Thank you.